they will take it further to scale it up. So up to pilot scale, even more than pilot scale, we work. And can read that, right? Research Center for Powder Metallurgy and New Materials. So powder metallurgy and new material is our core area. So when I say powder metallurgy, people will understand, but new material is open, right? So we work in ceramics, both oxide and non-oxide ceramics. You know satellite, right? Satellite has a mirror. There is a concave mirror. Usually satellite will be shown in the news and all. It will come with a one concave mirror. That kind of mirrors manufacturing facility we have with the ISRO collaboration and all. So that comes under ceramic. That's silicon carbide mirror. It's not mirror means what you see, that it's a silicon carbide, finely, smoothly finished concave mirror, right? And we work in sol gel technology. I hope you know sol gel technology. This glass, you have specs. People who have specs, you know, anti-reflective, right? That is all sol gel technology. So there will be a nano suspension polymer and inorganic and organic polymer liquid, which will be dropped on your glass and rotated, spin coating they call it as. And they'll make a nano layers of 6 layers, 7 layer, 8 layer. You might have heard in optical shop, they will say it has anti-reflective, anti-glare, anti-scratch. Those are all layer on glass, layer on polycarbonate. So that is a sol gel technology based coatings. So we are in coatings, and we are in one more surface engineering division where you might have heard in your aerospace lab, there is a aerofoil vanes. Those vanes are exposed to high temperature, up to 600. If they are near to the burning point, if they are little away, they go up to 200, 300 degrees centigrade. So when we say 600, 700, and near there at the core, they will be much more higher, 800 and all. So metal will accumulate heat and it will shape its change. Aerofoil will not become no more aerofoil. So to protect the metal, it has to be metal, yes, agreeing, but metal has a melting point, right? So it will accumulate, it has thermal capacity, right? It will hold. So to stop that interaction, there will be a ceramic coating on that, right? That is called thermal barrier coating. So it's going to be a white paste which will put that. So that kind of coating have many challenges in real-time application. So that technology we have in our ARCI, and we give service to GE also in that direction. And there are alternative to conventional coatings in the similar application. So CVD, PVD, and there are many other things. And even we have facility to micro arc oxidation coating. That's a coating division, sol gel I told. So like that we have different verticals. We have nanomaterial division, and you know missile, everyone knows, right? So missile has a dome. That dome is made up of spinel. It's again carbide, I mean ceramic, okay? So spinel, it's a special material which will allow particular wavelength to communicate. So when missile launches, then you will decide where it should hit. So there is a moving target, or no, after launching missile will change its direction and all. That communication has to be done by some, you know, electromagnetic waves and all. So those waves, that dome is sensitive to only particular wavelength. In that wavelength, we will communicate to the missile after launch. So that material, that dome, we have a technology indigenously developed in our one of the center, and it transferred to BEL. Now BEL is producing continuous production of those domes for Indian defense requirement, right? Entire factory kind of, you know, it's a big facility, has been transferred to industry for continuous production and supporting the defense requirements. So, and there is one more next level is being under development. It will be have 2 wavelength sensitive. So that is advanced dome for the application, right? So these are the another vertical, and we have solar vertical. We do work on solar energy, solar materials, and we have battery related center where we make lithium ion batteries similar to lithium ion batteries, and solid oxide fuel cell, hydrogen oxygen fuel cell and all, right? So these are all different particles what we work in ARCI, and one of them is carbon materials, and I am coming from laser processing of materials. So in laser processing of materials, we do laser cladding, laser surface engineering, laser welding, and laser micro machining, and pico and femtosecond lasers we have. It's a high-end facility we have in ARCI to support some very critical and niche requirements of industries. I don't know how to tell that, if you can understand. But anyway, so we can make a feature of 10 micron depth in on a component. So where you have, okay, you are seeing this internal combustion engine, piston and ring. So there is a wear problem. There is a temperature rise, and lubricant is not staying there in where it is supposed to be, because it's always in angle. So there we have a technology called surface texturing of a cylinder liner. That texturing, when I say texturing, your hand has texture, so it's very fine, but it looks like a smooth, but if you zoom in and see, you have some texture. So that kind of texturing, dimples we made on the cylinder inner liner, and then that is holding the lubricant, and if there is any debris, that debris is sitting in that pit. So that pit is of size 10 micron. 10 micron diameter, 10 micron depth. So that kind of patterning are possible, and it's demonstrated as a funded project. So it helped almost 2 times, 3 times better than the lubrication with and without dimples. So that kind of things are also possible, and I am in that center. I am working on laser related manufacturing called additive manufacturing, right? So when I say laser additive manufacturing, from the previous lecture, whatever you understood, I want you to say something. What do you mean by additive manufacturing? Anyone?
Loss of labor. Is it loss of labor?
Layer by layer what?
Deposition of
Deposition word?
any polymer, any metal, where we can create complex geometries with higher accuracy and less material wastage.
That is any manufacturing process. Additive manufacturing. Yeah. That word itself has adding material. So what is the opposite to add? Is there any subtract manufacturing? Yes? Who is saying yes? Yes, it is there. Yes. Who said yes? What is that? Any example of subtractive manufacturing? That's all. Machining, right? So their accuracies are how much? Can anyone tell what kind of accuracy you can achieve in CNC machining or lathe machining, whatever you say? Huh? I'm talking about accuracy, dimensional accuracy. So if I want 2 mm diameter, will I get 2 mm diameter? That will be always question in manufacturing and quality check. What is allowed, what is not allowed. That is anyway a different subject. Let's not get into that. So let's stick to subtractive manufacturing. There is something called subtractive manufacturing. There is something called additive manufacturing. Why the name is additive manufacturing? Because there is already subtractive manufacturing. They are taking it as additive. So what is the difference? Subtractive manufacturing and additive manufacturing. Don't tell now, sir, there I will subtract material. No. Tell something which make it sense. What is the difference? Now subtractive manufacturing is there. The example also. Now you tell me, if I have 2 options and 1 component, which one you will choose? All of you know additive manufacturing, right? From last 1 day and 1.5 days you are learning. So let's assume that you are now okay to make some decisions. You have a component, There is a subtractive manufacturing, lathe machine, whatever 5-axis CNC, high-end 5-axis CNC you have, and now you have additive manufacturing machine, process, whatever. Let's not define whether it's a polymer, plastic and all, okay? So you have a component to be made. So what is that? You will ask first question to choose whether it should go here or whether it should go here. Complexity, yes, but very open. Can you be, okay, let's keep complexity aside. Is there anything else? Good.
Number of products, ratio of number of products, mass production.
That is okay. We'll come back. We'll come to that separately. That will take another topic. Complexity will another topic. Yeah, these are the points. But now at this stage, as a basic, what you understood, I want to know. Material, yes. Anything basic. Don't go too much. Accuracy. That is again one next level. What she said makes sense. Hollow. What do you mean by hollow? Can you elaborate so that people will understand and bring some more points? It's okay, no, sir? Interaction is okay? Okay, fine. Because I should not be like it. Madam, you are correct. Sit and tell. Hollow. It's okay.
Hollow needs to subtract material, so
Okay, you are telling if it is hollow, you should go to subtractive. Okay.
once if we started with a single component and we need to have it, then we go subtractive.
Single component, subtractive manufacturing. Additive, other way. Tell.
To add something for
To-
component, we will go with additive and we need to subtract unit component.
You said something hollow. What is that? Huh? It's okay. You said something hollow, right? You said, right? Huh? Elaborate it. You didn't expect that back, right? बोला बोलो छोड़ दिया कुछ तो बोला हाँ anyone
Products can be made as single part.
that is the best point. Single part component means part integration, but that will give one more question. Why it was different part? Why you want it to be one part now? One material, one piece. Additive manufacturing is the solution. Understood what I am saying? So now you see many engineering components has nut and bolt, gaskets, flanges, right? Welding, riveting. Why? You want it or you have no other solution to have it?
Yes. We have no solution.
Welding is nobody wants welding. You are studying that as a subject, right? But nobody wants welding. No engineering components requires welding. If you are avoiding welding, they are more than happy. Because welding will add complications instead of, it will give solution. Yes, it is joining two components. But why you want to join first of all? Why? Why welding came into picture? At that time, no additive manufacturing was there. Let us assume that. Okay. And subtractive manufacturing was there. And welding came into picture. Why?
Unable to make single product.
Yes. So, what she said hollow. That comes to that point. So, there are hollow features inside. In conventional subtractive, how you will go inside and machine? Right? You can go external. You can take a big block. You start giving a shape to the block. But you can give inside hollow only when it is axially symmetrical, right? One side full open. Those kinds of hollow you can make, but entire hollow like ball kind of thing, how you will achieve that? Then you have to make two halves in a ball, make two halves, machine them properly with maximum accuracy possible, then put them together and destroy it by welding, right? So welding में क्या होता है? Again, you have to prepare the edge. Then is it third material being added or not added, right? And lot of heat input. I'm not saying welding is bad. If it is mandatory, you have to do. And there is a technology, by itself, well defined. If you follow that, nothing will happen. It's all good, right? But if you avoid that, if you can avoid that, that is big achievement in the industry, because when I am saying more parts in a one assembly, so many inventories you have to maintain. See, if you are making 2 or 3, it is not a matter. But in industry, they have to make hundreds in one shift. So 100 into, suppose 10 components are there. Okay, let's 2 components are there. 100 into 200 components, that 2 lines, production lines will run, right? And if they can't produce it, they will outsource it. If they are only assembly like Dell computer, bring one from here, lowest L1 here, L1 here, ठीक है, दोनों को लेके आओ, फिर बैठ के असेंबल करो. अगर उसमें से अगर एक प्रोडक्शन लाइन में थोड़ा सा एरर है, if there is small error in one production line, this guy is making perfect, this guy has some error in that shift particularly, right? So these are all the problems. So if you avoid number of components, so you are helping. One is inventory, because see, this is in Andhra, this is in Telangana. Half part is coming from Telangana, half part is coming from Andhra. Now there is a strike here. Only half part, what you will do? So these are the practical problems in the industry. So that's why they always choose something nearby, and they always create a nearby new one. Okay, you be there for us. So those are all challenges as of now industries are facing. So if you can avoid that by additive manufacturing, but additive manufacturing, as you said, numbers, it's not in, as far as metal is concerned, it's not in a production as of now. If you want people who tried production, or like GE, Airbus, they are all very big, they have huge capital and they can do that. But yeah, in automotive parts, I want 100 parts per day. Can you produce? If it is small, yes. If it is big, no. It's not economical as of now. But somebody said material. If a material is not conventionally manufacturable, somebody said wastage. If material is so expensive that conventionally I can't afford losing it, right? Somebody said complexity. Yes, if it is so much complicated that my casting pressure, suppose pressure die casting is another process, casting is another process, subtractive is one, shaping is another, right? Casting and all. So there casting, you have to make so many core pins, inserts and all to make complicated part. So maintaining that production is very difficult. So all those challenges, if you want to address, then additive manufacturing is one solution, one of the solutions. Okay, so what you understood this discussion? Is it additive manufacturing a solution for everything? No. If a component is very simple, affordable, can be done nicely with the conventional manufacturing, go by it. Don't push that into additive manufacturing. But when you are coming to additive manufacturing, your yesterday's lecture, design for additive manufacturing, if you can add some designs, extra feature which were not done because of thinking that it will be done conventionally. The components what you are seeing as on date are all designed thinking that it will be conventionally done, right? So now because you have additive manufacturing, added features in manufacturing, design and all, so you have to think away now. So you don't have to think conventional machining here, I have to make in 2 parts, so I can't make this here now, so let's make like this and section here and do this. But now you don't have to think all that, you have to think the requirement. End requirement, what is required, accordingly you design. Don't think which manufacturing process, then you decide what is the best process. right? But this doesn't mean that additive manufacturing has all the solutions what you are facing in conventional. No, it also has some limitations. So you have to understand limitations before deciding which process is best. Material, yes, and sometimes dissimilar material, yes. Somebody said adding features on existing component, additive manufacturing to some extent, yes. Load bearing capacity is all design part. So those are things are there. That is what he meant. Is porous structures and design the porous structure so that minimum material, maximum load bearing. So that comes under DFAM, design for additive manufacturing, right? Understood? Let's start my lecture. Okay. So that is the additive manufacturing what we are talking. So when I think somebody might have covered in the previous talks, but let me touch upon this. When I say additive manufacturing, what we are doing? We are adding material to achieve some shape. Yes. Any example other than engineering? Yes, but in your social life, any additive manufacturing you saw is happening around you. It's been happening. This room sitting here, is it? Yes. No, that is the example of additive manufacturing. But before that also we were practicing additive manufacturing. The civil work, this room, brick by brick, they sinter, then they add, they sinter, they add. But only thing is they take months. We are talking here hours, right? So now if you go to your 3D printing, plastic 3D printing, you have 3D model, you slice, then you think and all. But when this constructions house are all since ages, they are doing additive manufacturing, and computer was civil engineer in his head. He will imagine, okay, this building will look like this. Let me make this like this. Support here, pillar here. Support structure is a pillar. And when they are making this ceiling, what they do? They give bamboo support or iron support, and then they put reinforcement, then they put the concrete, and then they remove the support. Then you have this hollow. Same thing happens in additive manufacturing. Right? Or you avoid. You saw many house like this. Right? They may not need, only the concrete is liquid, so to hold the liquid they need, otherwise they don't need. Right? So that's what is, you will see support structures and all. So that is the best example. In olden days, they used to caves. You saw, no? You go to many historical places, you will see caves. They were subtracting. They were digging the rocks. They were making a space inside. Slowly they understood they can make something like this. Same rock, small pieces, they started constructing and they made a house, right? Yes, simple example, understood? So now next question. So if you are adding something, making something, so what all you need? These are the three things you need, right? One is, what is the minimum building block? What is that which will bind it? And what is that which will bring them together? Three things: material, binding material, then process which will bring them together. That together makes you additive manufacturing. So you have to have three basic knowledges. So what is the material? Whether it is a metal, polymer, first define that. If it is a metal, in which shape it is, wire, powder, sheet, right? And then binding, it can be bind by melting and fusing, it can be bind by sintering, it can be bind by binders, right? And there are many other processes. You can use UV light also to bind them. And friction stir welding, somebody might have talked. So there is another method of plastic deformation which will bind the material, right? That is a binding method, and then bring them together is a process. So when I say all these things, you will end up with all discussion and arguments and all. There are 7 basic methods. They found that, okay, these are the 7 additive manufacturing methods which will be, whatever you say, it will fall under one of these 7. Whatever method you say, mera ye hai, mera, it will fall under one of those 7. That's how they classified it and they gave a name. So that depends upon material form, means wire, powder, sheet. Then you have binding method, like melt and fuse, right? And sometime what is the energy source, like electron beam, laser, plasma, wire arc. WAM, wire arc additive manufacturing. The arc is the energy, wire, material, arc, additive manufacturing, WAM, right? So powder bed fusion. So powder made bed, then fused. Fused means melted by laser. It's a laser beam powder bed fusion. Electron beam, it can be a plasma arc, right? So like that, based on that they classified it. That's why you will see PBF, powder bed fusion. Under that you will have 3 energy source or 2 energy source, right? So it will be electron beam powder bed fusion or laser beam powder bed. And now I said powder bed means powder is spread. Instead of spreading, I will feed the powder. That will become DED, direct energy deposition. Okay, understood? So I told basic things, how you can see the classification, different types of additive manufacturing based on the shape, energy source, and how they are being brought together. How they are brought together, I told feeding the powder, feeding the wire, or spreading the powder, right? So that will make a technology. So how you are bringing them together, you have different models, OEMs telling that my machine is best, my machine is best, my technology is. So it's all combination of this. Okay, shall we move? Any question here? So now I will ask FDM. What is the binding? What is the material? Do you know FDM? Fuse deposition method. You have plastic machine in your college. What is that technology? That is material. Then binding by fusing.
We have layer upon layer of
Wire is being melt and placed on previous layer. So that 2 layers are binding by melt solidification. So fusion and solidification by electric heating. That is different purpose. The base is how much? 200 degree, 180, 150 degree. Preheating bed? No, preheating bed will not be there in FDM. It may be some, I don't know how much it will be. I'm not expert in that, but I don't think that will help. But for what purpose it is? Right, it's not for
building the lattice structure for complex.
Fine, but purpose is what? If you don't heat, what will happen? If you don't heat it 60 degree, what will happen?
Basement will not hold.
But why? No, you are saying what you see. I am asking one layer behind that. You are saying, he is saying we need temperature. You are saying if you don't heat, it will delaminate. Now question is why?
Because the temperature difference between the new layer and the old layer will be quite close to it. Otherwise,
right. So ultimately residual stress management, thermal expansion coefficient difference, right? That has to come. If you know that, now when you are choosing new material, now you know PLA, this is needed. Now suddenly new material came which you didn't know so far. Now you want to do it. Will you heat again 60 degree or not? Who will answer that? The expansion coefficient of the material will answer that. That is a intrinsic property of material which the material supplier has to say. Whether it is a 60, whether it is a 80, whether it is a 40, we will decide that depending upon that value. Just one, then that will become MTech project. If you ask one more question, it will become PhD topic. Right? So like that, if you have 3 questions in one process, your PhD is done. Right? So yeah, that's a thing you told. I hope you understood. So let's go to next slide. This is about metal powder bed fusion, right? So I am focusing on this technology now. I told many things. Now let's come back to one point. It's called powder bed fusion, means you spread the powder and fuse it to achieve the additively manufactured component. Okay. So can you see here two processes? One is like this, one is like that. So what I am trying to say here is, you are spreading the powder. This will go up. Can you see this side, people? This will go up. There is a powder already placed in this part of the machine chamber. This will go down all the way. There will be loose powder tapped, stored in here. This is in inert atmosphere chamber. This will go rise and makes the powder extra here. And this is not a ball, it's a rod. Okay, it's a rod. So this rod will take this extra powder and spread here. By that time, this will move down. Initially this will be here and this will be here. So this will feed the powder, this will spread the powder, and this powder will come in this side. So now how they are moving? They are moving by your slice thickness. Okay. So this will move down by slice thickness. So new step will form here of a layer thickness. This powder will fill that gap step. Extra powder will be collected, one more chamber like this here on this side. That is not shown here. Okay. This is a powder bed fusion. See why I am talking so, what is there sir? Oh, aayega, aapko kya karna? Right? I will tell you why. So this is a laser. Laser is scanning here as per your layer number and pattern. It will melt. This black is melted part. Okay. This is loose powder which you can use it later. Next build you can remove it and sieve it and then use it back. Okay. Why I am explaining so much? Can you spread your atta, chapati atta or something? Can you spread? How uniformly you can spread? Question is spread, yes. How uniformly? That's where engineering starts. How uniformly you can spread? And how, okay, I spreaded uniformly. Yeah, this is perfect. Repeatability. How many times you can do that? Same.
The hand it is not possible.
No, whatever you use. I'm not saying hand and all. These are things will matter a lot. And what I'm talking there? I'm talking 50 micron, 30 micron. Can you imagine 30 micron? You have paper in hand. What is the thickness of that paper? 70 micron? Right? So it's in 100 micron range, right? Less than 100 or maybe around 100. That much thickness I am talking. That to loose powder I am spreading. And if somewhere I make 50, somewhere I make 60, somewhere I make 80, will it work? No. Because my melting parameter, laser power and speed are tailored for particular material thickness. So if I don't follow that, somewhere I will get very good, somewhere I will get not good. What is not good? I will talk in next slides. But understand that. So somewhere it is more powder, somewhere it is, so one layer it is more powder, one layer it is less powder. Right? Are you understanding what I am saying? So these machines are tuned to 1 micron variations. So 20 micron means 20 micron it will move. 20 micron powder will 20 micron filled by powder, and laser will scan with the same defined powder for all the layers. Okay. So it's happening or not, that is a different question, but it is designed like that. Right? So that is where we need people to think to that kind of dimensions and design the machines like mechanical engineer, you people, and have your indigenous, facility of doing and executing such a process. I can say, that will go down, that will go up, that will happen. But I'm highlighting, I'm pinching you so that you'll understand that these kinds of accuracy you have to talk. It's not just a machine, wo ho jayega, nahi hai, aisa nahi hai. If it is not moving also, we have a problem. We take care of the machine, we calibrate machine every year to ensure that it's happening what we are saying. We can say, but is it happening? Right? So all those things, but here another technology here. Here powder will be stored here, not in the chamber like this. So you can add powder anytime here during the process. The powder, defined quantity of powder will fall, and that will be taken by this slot. Can you see this slot? This slot will match here when powder is dropped. So powder is stored in this. When it is moves this direction, this bed, can you see here? This will go down. Powder is spread, and some more powder is there, that will come back. When coming back, it will spread. So in this case, we have two directions spreading. You can save a lot of time, right? So now, what time you are talking? What time? Can you imagine when I say 50 micron? Let's take 50 micron, okay? 50 micron, and I am building 100 mm component. 100 mm is what? This much? 10 centimeter. This much component only. 50 micron. How many layers? Quickly, anyone?
It will be around 10 power 4 layers.
No, that is too much. Calculate again. 10 mm. 1 mm is 1000. 1000 divided by 50 into 10.
10 centimeters is the total length.
100 mm, sorry, 100 mm, not 10 mm, 100 mm. That again one more 10 into multiply by 10. So those mean thousands of layers, right? Can anybody give number? अरे मोबाइल है यार, निकालो फटफट मारो क्या?
If it is 10 mm, 200 layers.
10 mm, 200 layer. Correct, no? So 100 mm will be 2000 layer. That's what I know that. So 2000 layers, right? 2000 layers. Are you agreeing? 2000 layers. So 2000 times this will move to and fro. Now there is something physically moving and spreading your 50 micron. It is not that fast. It will go right. So at least 10 seconds per and scanning some more 5-6 seconds. Let's take 20 seconds per layer. 20 seconds into 2000. How many hours? Right?
11 hours.
11 hours for component. So I'm not saying good, I'm not saying bad. I'm giving you some numbers. What I am talking, how it matters. Right? सर उसमें क्या है, 50 माइक्रोन को 100 माइक्रोन कर दो, आधा हो जाएगा टाइम. Can we do that?
Accuracy matters in that case.
Its accuracy is different question. No, I am not at all coming to engineering. I am coming from process side now. So that we can do. Whatever I said, 50 से 100 कर दो, लेकिन 100 से 200 नहीं कर सकते, 50 से 200 नहीं कर, 50 to 60 कर सकते हैं, 60 to 60 तो 70 ऐसा प्ले कर सकते हैं. लेकिन लिमिटेशन क्या है? What is the limitation is the laser power what you are using. That it already came with the machine. Like you have CC bike.
I was about to ask that, sir. If you go from 50 to 100, should we keep the laser power
We have to change, but how much you will change? Right? You have already 250cc bike over. अब 300cc एक्सपेक्ट कर रहे हो तो फिर इंजन चेंज करना पड़ेगा ना. So you have to change the laser. When you change the laser, you can't just keep on adding power to the laser because your spot size also will have limitation according to the power, the many combinations, right? So I have usually these machines come with 400 watt laser, 500 watt laser. right? Whatever I optimize in my machine, I can use it on 500 watt laser also. But if you say 1000 watt laser, there are machines with 1000 watt laser, but their spots are different. Their energy distribution in the laser's spot is different. They are all different purpose. As you said, features will, again you will lose some features because particular pattern lasers distribution will matter a lot. Okay, fine. Now I will just go away to this process to another process. So what if I increase the spot size? Now I told spot size, laser power, all these things. Now I will change the laser, I will change the spot. Can I increase the production rate? Can I reduce the time, build time? And what is the compromise? Right? So features. What is the process you will go if I don't want powder bed fusion? Features are okay for me, I compromise on features. What is the next process you will upgrade it? You may not be knowing, so that is the EBM, but you will know DED, that next level, direct energy deposition. So I will tell you simple correlation. Do you know DED process? Direct energy deposition, do you know? Nobody told in the previous lecture? Anyone? Raise the hand. DED. Lens, laser, engineer, net shaping? No? Okay. This is, you know, this is powder bed fusion. Now you know this. Okay. Here powder is spread and pre-placed. DED is somewhere where powder will fly in a nozzle and it will come and converge with the laser. It is like your pen. Your tip is also going and ink is also coming simultaneously. Right? Like that, laser will come, powder will come, they meet at one point and robo will, or the head will move and there will be a deposition layer. Are you understanding? So there is something called electron beam. Instead of laser here, electron beam. Rest all is same. And the entire thing will be in vacuum. Because it is in vacuum, some limitations will come. There you will lose some advantage of powder bed and you have to compromise with the feature. Do you know pencil? Sharp tip pencil? Let's keep it fast. Okay, pencil. You know pen. You know sketch pen. You know highlighter. Right? I will correlate this with the different technologies. Okay. You know WAM, wire arc additive manufacturing. Yes. Now you know DED, what I said. You know EBM, same process with electron beam, and there is something called what I am talking is laser powder bed. So I will say pencil. पेंसिल से क्या कर सकते हैं आप? अगर मैं इतना बड़ा ड्राइंग दूंगा तो पेंसिल से भरो बोलूंगा, fill it with pencil. How much long it will take? Whatever. How many hours we got? 11 hours. 2000 layer, 11 hours, right? So 11 hours you will take by filling with a pencil because pencil tip is very thin. Yes. Now I will change pencil to pen. Same drawing I will give. How much time you will take? Right. Now I will remove pen, give you sketch pen. Time is reducing. I will give you highlighter. Time will reduce. Now your boundary is complicated. And how nicely you can cover the boundaries? With pencil or with sketch pen or with what? Pencil. You need pencil, but you need highlighter. Right? Where you want to do fast, but cover the feature. That is not going to happen. That's what I am trying to say. So all these processes are different, as your pen, pencil, sketch pens are different, but they are coming with their own limitations. I can't have small eyebrow if you are making a person's face with a sketch pen or highlighter. You have to use pencil there. But I don't have option in additive manufacturing. Okay, fine, I have all the lasers and all the tools. I will use whatever I want. Right? So here, this process is the smallest spot. So it's a pencil. You can say LPBF is a pencil. Pen is electron beam. Same technology with electron beam. Because it's under vacuum, I can't use fine powder. I have to use coarse powder. and electron beam is not easily coupling with the metal, so we have to use some other extra things, so that will limit the feature. You can't achieve all the features what you achieve in this process if you change laser to electron beam. So I am telling it as a pen. Okay. Now sketch pen. Anyone? DED is a sketch pen. Because laser source is there, properly it is coming, defined source, and feature, the depositions are very thick, and here I am taking 50 micron, there you will talk 300 micron. 50 to 300, 6 times. 6 times build rate increase means 11 hours has become 2 or 3 hours. Right? So that kind of, what I am taking is that, because your layer thickness is increasing, 50 to 300. Now, no, it's okay. It's a ship ka part hai. A big ship. It has big parts. I want to make that. Even DED also will be slow there, because ship ka part itna bada hai. How features? How does it matter? It may have some hole, through hole, or some threaded hole that you can do anyway later. There you have to use WAM, no, wire arc additive manufacturing, or laser wire additive manufacturing. Right? There wire will come, and arc will come. You will get very huge melt pools and all, but it will be fast. Understood? Am I making any sense? Are you understanding? So now if I give you a component, you will decide which additive manufacturing process you will decide. Yes? That's what I told. No, ship ka part hai, tanker hai, military tank, uska ek part hai. Kaise banaoge? WAM. Right? And when I am saying this, anybody notice something? I am telling I will make something near, and then I will bring it to my dimensions. Means you need conventional process also. So additive manufacturing is not replacement of conventional process. They are complementing each other. Okay? Fine? Agreeing? So let's go with that understanding. Don't think that okay, additive manufacturing hai to ho gaya, sab kuch aa gaya, ho gaya. Nahi hoga. ठीक है? So you have time limitation where you are getting easily features everything, but if you want make a big part, you have to go for other process where you have to depend on conventional manufacturing. Right? And there are many things here also we need conventional manufacturing. We always keep some tolerance. That's why I was initially asking accuracy. CNC accuracy talks in 10 microns. Correct? Am I correct? Anyone you have experience with CNC here? Any faculty? They talk 0.01, right? Plus minus 0.01 kind of things. So here we talk 100 micron, 0.1. Because laser spot, what I am talking here, the minimum what we can use is a 50 micron. Now my question is, I will give you 50 micron pencil tip, draw a line. What is the thickness of the line? Who will tell? 50 micron? Sure?
If it is on the paper and if it is just a straight line, it's not layer by layer added.
No, it's only one line. Okay, I will change the paper now. You have very good bond paper. Now I will give you newspaper. Same pencil, ink pen, you draw, it will spread. Right? So melt pool width will come into picture. So all these things will add to your problems. Aluminium melt, it will spread nicely. Steel, it will not spread. Same melting parameters, right? Same line. So paper, जैसे आपका ink pen है, आप paper different paper change करते हो ना, वैसे वो width change हो जाता है. So that means different material also you have to take care while considering all these things. Am I doing aluminium part? Am I doing steel part? Am I doing titanium part? That also matters what you have in hand. Fine. So now let's come back to our pencil example. So you have such a big drawing, you are filling with pencil, and you have sketch pen, you are filling with sketch pen. Where you will find more defects? Defects, I am talking defects. You will overlap to cover the area, ओवरलैप प्रॉब्लम कहां पे ज्यादा है? वेयर ओवरलैप प्रॉब्लम इज मोर? स्केच पेन इज मोर इजी, पेंसिल में प्रॉब्लम है. If you zoom in and see your pencil drawing, how many white spots you will see? Yes or no? Because it's a thin line, overlapping is difficult. थिक लाइन आप 10% भी ओवरलैप दे दो कवर कर लेगा. हाँ, बॉर्डर का इश्यू रहेगा वो अलग बात है. बॉर्डर का इश्यू हर जगह रहेगा. लाइक यू मेक व्हाट इज दैट, बोट्टू, मॉर्निंग घर के सामने लगाते हैं ना बोट्टू. हाँ, वो डॉट डॉट मुग्गू. हाँ, डॉट डॉट लगाते हैं, बाद में उसको यू विल जॉइन देम एंड देन यू विल फिल कलर. यू विल बी कंफर्टेबली फिल व्हेन इट इज बिग. स्मॉल हो गया तो हाँ वो प्रॉब्लम रहेगा. हियर आल्सो वी आर डूइंग सेम. when it is a mesh means your first component आएगा तो design 3D model, you will mesh it and you will slice it. Those mesh will look like a dots. Those dots are nothing but your that are joined as a border. Then you will fill inside with the laser melting. So same thing we are doing what you do in the morning in front of you, right? So same problems will come here. So until you get, how many times you overlap to get your color uniform? So where it is more easy, big, comfortable, but when it is small, it is. So where you will use small channa and where you will use big channa, that there are different channas, I know. If I am correct, I don't know, right? So those things are there. So that's how you have to choose your process. You have to choose your laser source and spot size and build rate, component कितना बड़ा है, क्या फीचर है, स्मॉलेस्ट फीचर पॉसिबल है या नहीं. So when I say I have 50 micron spot size, but what laser we have in ARCI in my facility is 80 micron spot size. I can't go less than 80 micron. So if I'm using 80 micron one line, if I do, the minimum I'll get is 80. The maximum I'll get 300 also, depending upon the material I am putting it there. If it is aluminum, 80 micron line will give me 300 micron width line. Laser is 80 micron, but melt pool I got line is 300 micron. If it is a steel, it will be 110 micron. So it is more than the pencil. So when I am saying my tip itself is 80 micron, what is the accuracy I can talk? Understood? So I will talk at least 80 micron. So 0.08 and we are talking CNC 0.01 and all. So that's why what we do is we make a component, we give allowance, we machine that later. Allowance जो भी 100, 200 micron हम will give and then that will machine and that will fit in assembly where the conventional part is made by conventional process CNC. So that will have accuracy of 0.1, 0.05 or so. So that will fit into this because this is also machined again. The counterparts are machined by same machine, right? So when I say I will use post machining, post process as a conventional machining, the reference is always matters. Do you know referencing? Okay, first of all, CNC you have to understand. As a mechanical engineer, you should know what is CNC. Please visit nearest any fabrication facility and understand what is CNC. Okay, that is very important. So if you know CNC, I will understand what I am talking. Then accuracy of fitting and all those things. Okay. So here that's what I am telling. So this is my single melt pool, right? Then if I add, then this is melting, then again this is melt and this is all previous layer, this is depositing on this. So when I say plastic, when you say it is a physical bonding, the next layer is not melting the previous layer, it is just sitting on it. But in metal additive manufacturing, it is a metallurgical bonding. Can you see it's melting here? This is a previous layer, this U is literally melting the previous layer and getting bonded. Plastic, if you tear it, it will come layer, layer, layer. But here you will not see that. If it is coming at the very poor additive, it's not done properly. So metal, you have to dilute like you are welding. Okay, so initially I told welding is always a problem, so we don't want it, but additive manufacturing is a bundle of weld. Okay, so that is another challenge with the material, processing kind point of view. Can you, what is this? This is a weld pool, right? If you have studied your welding subject, this will look like weld cross section. How many welds are there? So bundle of weld. So whatever welding problem you have in welding, same problem will come here.
Each layer is like a weld.
Yes, it's a weld. I am telling you, we don't want weld, but ultimately I am doing weld, right? So that's what is the metal additive manufacturing. So now, what is the question? Question is problem. क्या problem है? So whatever non-weldable materials conventionally are challenge for additive manufacturing, because it's a bundle of weld. Weldability is the issue. So if conventionally challenge है welding में, तो वो material here you will have here also problem. So if you are choosing a material for additive manufacturing, first question you should ask is material. Which material? Is it weldable or non-weldable? There is a graph of a material, weldability wise they will place it, especially super alloy material wise, super alloy steels and all. So you should know weldability of the material before choosing that here. If it is a really challenging, then you can say let's change the material. If it is okay, we can manage, then you can attempt. Okay, this is how the melt pool will be. This is a laser hitting and these are drops, right? This is how the other direction. So this is the melt pool. This is how the heat will be flowing. This is a loose powder which is about to melt, and this is a laser which is moving. Simple schematics, but talks a lot. This video, if you see, you will understand what actually happening. This is how the powder is getting fed. So this is the dosage. This is defined quantity of powder will fall in the chamber, and that powder will be spread. That is how the powder came into the process. Now you will see how laser is coming. That is the laser light entered. This is called vario scan. These are called flying optics. This is how the process happening in the chamber. Do you think so many lasers are there? No, it's one laser, it's moving so fast. Okay. So this is the part came out. There's a loose powder, what I said. Right? Okay, shall we? It's okay, enough? Any questions on this as of now? So let's go to my work now. What we did from last 5-6 years with some case studies. So far I covered process. Right? Anybody has any questions related to process? Now I will go a little fast. So this is what we have in the ARCI in my lab. So these are the two machines we have, and this is the electron beam, this is the laser. I told two laser source, two energy source, right? This is a machine with the electron beam. This is a two machines with a laser beam. This chamber is inert atmosphere. There is a chamber here. It's a vacuum. Okay, and these are the facilities for post processing, heat treatment and all. I told you it's a bundle of weld. If anybody knows about welding, you know they preheat before welding. They maintain some 200-300 degrees centigrade and then they weld. Sometimes they weld and then they do heat treatment. Why? Because bring back the normal microstructure anisotropy stresses induced by welding. Same thing we have to do here. I told bundle of welds. So we'll have many residual stress issues, solidification issues, and metallurgical microstructural segregations and phase segregation issues. All those things will be solved by post processing. Right? We have time now? I don't need. If they need, fine. Okay, fine.
After 5 minutes.
Another 5 minutes. Okay. Right? So we have characterization. So when I said metallurgical issues, we have to test them. Do you know tensile test you have? 3-point bend test you have. But there is something called X-ray, you know, XRD, X-ray diffraction, that is used for phase identification, metallurgical subject. Okay, you know ferrite, martensite, right? Those are all phases in iron, steel and all. But when you go to other material, you will find other phases. Okay, all those things will be identified by X-ray diffraction. And if you know the features and material, you can know it by SEM. You know SEM?
Yes.
It's called scanning electron microscopy. The SEM is a very basic instrument, but now there are many added features, FESEM, many things. There is something called EBSD, whatever I am written there. All these facilities are all high-end characterization, metallurgical materials characterization facilities we have in ARCI. This is something called atomizer. You know, I said powder. From where it is coming? So there is a process by itself. It's a 2-floor. Now from top we will melt, then we spray the melt. Spray means what? You know, you have spray, like you know during COVID time you use spray, ethanol spray and all. Same way, bring the liquid and with a lot of pressure you spill it out. Like take water in mouth and do. Same thing we do. Metal melt. So it will become drop in a confined atmosphere. It will solidify and drop. And when it is coming, obviously it is free fall. It will be a sort of spherical. We optimize it so that it will be spherical. Otherwise, it will be a drop. Right? So that metal powder we sieve, and particular size will be used in this process. Particular size will be used in this process. I told DED. There again different particle size distribution we need. All are powder but different size powder. I am not getting into that, it will be too much for you, but just understand the powder particle size, it's not same powder everywhere. Material is same, but powder size distribution will be different. Okay? So we have softwares and we have reverse engineering facility here, and this complete thing will start from material development to component design, manufacturing and raw material production also. Right? So with this facility, and this is another thing we have, this is called DED. I told you DED, right? So this is something similar to DED. It's called laser cladding. If you put entire thing in an inert atmosphere, that will become DED. But the laser what they use will be much finer. Here we are using 2 mm spot size. Will give 1 mm thick. Every layer will be 1 mm. I told 300 micron, right? So that is a different, you know, much more near net shape. This will be little rough, but better than welding, means wire arc additive manufacturing. right? And this is a WAM, wire arc additive manufacturing, with a CMT. Can you see here CMT? It's a cold metal transfer technology. It's not TIG, MIG. It's a CMT. You know TIG? TIG, TIG welding. You know MIG welding, MIG. This is next version is CMT, cold metal transfer. Yes, note down CMT. You can search and look into it. It's a very interesting technology.
So is it cold metal welding done in space? Where they
See, CMT is the latest technology where you will get minimum heat affected zone and substrate where you are joining two materials, right? The material should not get affected by the heat you are putting during welding. So it's a cold metal transfer. It has a better control on heat input to the plates which you are welding, right? That is welding. But if you deposit same on same, that will become additive manufacturing. WAM. You can have a control robo and all. So we have all these facilities in ARCI in my center. This is what I told, atomizer 2 floor. So can you see a cylinder, argon cylinder? If you that will be this much height. So that is standing here. One floor, then one more turn here, then one more turn here. So here we will melt the ingots, rods. Then that will be sprayed in this silos. Then it will be collected. Two fractions will be collected. One fraction here, one fraction here. Then we sieve it. Then we will separate the fraction and then use it accordingly. Okay. So these are all different challenges. I am not getting into metal powder challenges. What will happen if parameters are not optimized? There are many issues. So I told you defects. When you zoom in your pencils filled paper, you will see some white spots. Those are nothing but porosity in additive manufacturing. The smaller the spot size, more porosity. It's inevitable. Only thing is you have to optimize nicely so that you will have minimum porosity. So zero porosity assuring is very difficult. Okay, and that border issue will come when you are filling this thing. The same border issue will come. Whatever you try, there will be some border porosity. That's why nobody claims 100% dense part in additive manufacturing. 99.5 people say to be on safe side, but they will be much higher than that, but not 100. For that they will do post processing HIP and all. Then they claim 100%. But during that process, there will be many metallurgical changes in the built part. It is good sometime, it is okay sometime. Okay. So these are all powder characteristics. So when you make the powder, if you are getting this, then it is very good. But it's not always you will get this. You will get sometime this, sometime inside porosity, broken particles, elongated particles. These are all defects in powder making process. But what we want is this or near this. This is satellite, you know, Earth has moon as a satellite. So like that you will have satellites here which are stick to that. That also we don't want, because we are spreading. The more spherical it is, better spreadability it will be, better repeatability it will be. Right? This is the packing. How? That's what I was telling you. Different size will matter. The fraction range is matter. So when you start with 16 to 63 micron, you will end up with no porosity because of the powder. Here 16 to determine the finer fraction, coarser fraction. This is the particle size we look for, because packing density. So how nicely they will get packed, and that much better they will be melted and spread, fused together, and minimum porosity you can achieve. This is another particle. It is hollow inside. The particle hollow inside. That is a gas entrapped in a particle itself. And if I use such a powder in my process, that gas will still entrapped into my component, and you will see as a perfect spherical porosity. If it is a perfect spherical porosity in cross section of additive manufacturing, that is gas entrapped. If it is a non-spherical means you can improve it. But it is a perfect spherical means you have to check your powder, or you have to check your inert gas flow, or change some parameters so that like that. No, it's a perfect spherical here. Can you see here perfect spherical? These are all from such a powder mostly. So this is what we do. These are all the different materials what we worked so far, about more than 15 materials. As a R&D, when powder comes to us, we characterize it, we do process optimization, then we do post processing, then we characterize, then we establish post heat treatment, and those are the 5 unique things what you should look if you are choosing additive manufacturing. So one is design freedom, second is part integration what we discussed, conformal cooling channel, hollow inside. Conformal cooling channel is interesting. I will come up in one case study. So light weighting and then dissimilar material. Light weighting, sir was telling that it will have good strength, but weight will be reduced, right? So these are the 6 different directions what we work. Design, DFAM, system modification design, don't worry about it, that is machine side development. Process development and post process what I covered in structure property correlation. Indigenous powder for AM means we make our own powders. All metals are not available in powder. Okay, and if I have a powder atomizer, if I have a company, what powder I will make? What I will sell? The more demand item I will sell. So I will not make all the alloy and make a powder and keep it. So depending upon the requirement I will make. If you come up and say I need only 10 kg, but why I will supply you 10 kg? I have 100 kg batch. So if I give you 10 kg, 90 वो कौन लेके जाएगा? है ना? तो वो loss आएगा. Otherwise you pay 100 kg cost and take 10 kg. Right? These are the limitations as of now in terms of metal additive manufacturing where powder is being used. So you will not get any material you say powder is available. No. You have to see what powder is available so that you will match it and get it achieved. Or you should have something what we are doing. We have a small atomizer 10 kg. So out of 10 kg I will get my material of 5 kg after sieving and all. So 5 kg one batch. So that much powder I will get. Even though that powder is not available in the market, I can take the rods and I can melt and I can make the powder. So that's the advantage what we have. So we play with different material, different applications that you will see in the coming slides. So that's where this is our own IN78 atomized in ARCI, IN625. This is a Russian alloy. This is a biodegradable alloy which we developed in ARCI, right? This is a hybrid. Hybrid is something interesting, dissimilar material component. Means one component is there. So far you are making this separate, somehow you are bringing them, riveting or nut and bolt something, you are matching them. But now we can build them together with a dissimilar concept. So this is a case study. I will not get into this, I already covered. So what I said, no single track we will make. So we make a single track to see continuous line is coming or not. See, it is a broken line here, broken line. So we should get a continuous line, that parameter we will choose. Okay, we'll spread the powder, we make one line, then we will see whether it is continuous or not, then we will choose that. This is the powder what we had. Can you see some satellite particles? These things are okay, but not all particles will have satellite. This is a distribution, this is D10, D50, this is a particle size distribution. This is the first experiment we will do in any powder we get. I am from research and development, so we always choose a powder which are nobody can touch, nobody have access to do that. So those things we do. This is a S13 tool steel, one example I am doing here. So what we will do, we will cut that single track and we will see how it is inside. I told you, no, there will be some metallurgical melting. So I am seeing that here, how much melting it is inside. I am putting graph, I am choosing the best which is suitable for my what I want to do, right? So these are the things which are fitting in my scope, process window. Then I am taking them here. Then I am choosing them in 0.6 range. These are the parameters I am choosing. That's how the optimization will go on. Right? Let me know when we have to go for break. Fine. Fine. Right. Let's meet back.
When we are dealing with these powders,
Being taken forward when you have completely new material. Suppose you are doing PhD or you have ended up with some project where I have new powder, what I should do, how I should start. So that's what I'm trying to show you with one case study where we have optimized and developed a parameter window, right? So first I told you how we will take the first initial attempt, then how we are converging to the window, and then we are cross section, then all these cross sections with the melt pool width to dilution, okay, that ratio we are taking, and that ratio is this depth to width ratio 0.6 के आसपास हमने एक window बनाया. So this window we are taking as a next level parameter. What is next level parameter? I have now single track. In a layer we have one track. Suppose you have a drawing, you made one line with a pencil. Now where you will put next line? Adjacent to it. What do you mean by adjacent? Can you define?
very next to the earlier one.
Fine. What is it? Quantify it. Good. It's good. Quantify it.
There must be some overlap.
Overlap. Right? Some overlap. What is that? Is it 10%? Is it 50%? Is it 30%? That we will see next slide. Okay? See, we have single track. We are putting next track. Center of the track to the center of the track. You have to think. So from where you will come with this dimension? Previous slide. We have single track width. I choose particular power, particular speed. I know for this power, this speed for this material. Whether it's a steel, aluminum, titanium, whatever. This is the width. Width ka half is a center. So that half, this half, that means zero overlap. Center to center is one melt pool width is zero overlap. That's what it is. Can you see here? One melt pool, another melt pool, center to center, zero overlap. So now if I increase that 25%, 50%, 75%, 100%. Understood? Now you just see the geometry. It's a simple geometry. What actually happens, you don't worry now. You understood that? Now you'll go to next level. I took one parameter from that. Can you see here? P5, P4. P5, V4. Means P5, V5 from the previous slide. If you go here, I don't know which one is that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Somewhere here. Or you'll go to previous slide, then you will understand. I think we change those numbers later. It is there here? No, no P5, V5. Yeah. So that is one of these. Can you see here P5, V5? This is P0 parameter star. This is P4, V4. This is P5, V5. This is P0, P1, P2 for me. Okay. So I took power and velocity, 4 and 5 combination. And I started H0, H10, H20. Can you see here? Can you see the photograph difference? Same power. I varied the hatch distance up to 60%. Forget about 100%. It's burning literally. Means that much energy density you are putting in. See here, this is further. Right? So where I should stop? I should stop somewhere here. So H20 is nothing but this 20 here. Can you see here? 99.5 density. 99.5% is what? It's a relative density, not porosity. Porosity is minus 100. Relative density is what? You know density of the material. What is steel density? Anyone? If I give you titanium one block, same block size aluminium, same block size steel. Now tell me which is what, and I will wrap them in paper. I will give you. Can you tell which one is what without seeing what it is?
By weight.
So now tell me what is that? That's what I am asking. Density. Steel density, anyone?
We must remember the exact value.
Tell me the range.
It has more.
Range, number. I'm not asking exact number. Tell me the range of number. At least tell one number which is in the range. I know the range. Okay.
4,000 kg or
If you reduce it to gram per cc, how much it is? 4,000 is 4 gram per cc? Something? No, I don't know. If you calculate, you will see. 7. Google है, Google करो, क्या problem है? No problem. Tell Google also, it's okay.
7,838.
हाँ, so that is in gram per cc will be 7.8. 7.8 gram per cc. हाँ, usually steel का 7.5 से लेके 8.5 के रेंज में रहता है, depending upon what alloy elements are there, right? Tool steel, S13 tool steel का देखो, करो Google, है ना, इंटरनेट नेटवर्क है ना? No problem, use Google, it's okay है ना? हाँ, right? 430 check करो, 430L. These are all different materials.
Stainless.
Stainless steel 430L. मिला? Iron 708 करो कोई और? Iron 708, एक Iron 708 करो, एक 430L करो. I'm just giving you, work so that you will understand what we are talking.
7.7 to 7.8.
Right? Then what is this thing? Titanium TI64. Anyone try? TI64. Just write TI64. T is capital, I small. TI64 density.
4.3.
Right? 4.3 gram per cc. Now, can you make a relation between steel and titanium? It's half. Can you say that? Now you remember. फ्यूचर में कोई पूछेगा टाइटेनियम का डेंसिटी क्या है, सर हाफ ऑफ स्टील. अब स्टील का क्या है, कुछ तो है सर, देख के बताता हूं. है ना? एल्यूमिनियम का क्या है, कोई भी ALS टाइटेनियम जी, कोई भी एल्यूमिनियम है, एक डेंसिटी डालो, सर्च डालो. Two point something.
2.7 gram.
2.7. Now it is half of titanium. Somewhere near. रिलेशन आ गया है ना? कौन सा लाइटर है, कौन सा हेवियर है, कौन सा मोर हेवी है? कोई आयन 708 का किसी ने किया सुपर अलॉय? आयन 718, I कैपिटल N स्मॉल 718.
$8.1.
8.1 है ना? This is super alloy. It's a nickel chromium super alloy. Okay, used in aero engine components and all, in space also. Somebody try C103. It's a columbium alloy. China, in world market dominating with refractory materials. 8.9 refractory material. Do you know? Refractory materials, columbium, niobium, those things are all, that is a alloy, C103. One interesting thing about C103, just to share with you, C103 is a material used in rocket or satellite positioning, converging, diverging nozzle. What is the weight of that component? About 150 gram, right? How much? 150 gram, 200 gram pakad. What is the block? Conventional machining, not additive manufacturing. Conventional machining. What is the block size they take to make that 200 gram part? Height is more. The design height is more. Weight is less. Understood? So they start with this much big block, almost more than 10, 15, maybe 20 kg or so. What is the cost of each kg? It's a refractory alloy, columbium alloy. 1 lakh plus rupees kg. When I heard long back, it's 78, 90, but now after China, US ने कुछ किया, China ने कुछ किया, तो refractory का पूरा cost बढ़ गया. This powder C103 powder I am buying, I purchased 2.5 lakh rupees per kg. You know what is steel powder cost? 3000 rupees kg. Maximum is 3400 rupees kg. What is super alloy? Super alloy, I told you, iron 718 and all. 6000 rupees kg. Aluminium, it's a health issue. If you atomize aluminium, it's little expensive. Only few countries are giving. Even we are atomizing in our ARCI. Somewhere around 6,000-7,000 rupees kg, because it's not many people are making it. Not because material. It's many people are not making it because of a health issue. So many countries banned aluminium atomization. Don't do aluminium atomization. Don't have to do. So you buy. Let other people do, but you buy, but you don't do. Right? So because it's health issues, their norms will not allow. So that's how it is. Understood? Got the idea? Different material, different cost. So they will start from that much expensive, that much volume and that much expensive, and they machine it. They will get 200 gram part. Now you ask, sir, 20 kg में 200 minus कितना हुआ? ये इतना expensive बोल रहे तो chip का क्या value है? Yes, they have to collect every chip. When they are returning back to ISRO, they have to weigh a part, they have to weigh chips, match it to the what they received, allowing some percentage loss, they have to return. Understood? Good example. Felt something interesting? So these are the alloys. There is one more alloy. Check 247 LC. Okay, check one guy check tungsten W. Do you know tungsten? All of you know tungsten? Where you will find tungsten? Bulbs. But these bulbs have? These bulbs have? Where you have resistance coil, no? There you will find it, okay? Tungsten density कितना है? 19. हाँ. So now you know the numbers. Gram per cc. Yeah? Remember the unit. Hello. Don't, as an engineer, don't leave units. Okay. You always come up with a unit. Remember that. Gram per cc. Whatever I am talking, all is gram per cc. 19 we talk. 8.23 we talk. 7.89 we spoke. 4.23 something we spoke. 2.8 also we spoke. The magnesium alloy. Anyone check magnesium alloy? It will be further less than aluminium. Do you know magnesium alloy? How many of you know magnesium alloy? Anything heard about it? Right? हाँ, aluminium से भी कम है. क्यों? Advantage क्या है उसका? Magnesium alloy? Lightweight. Have you heard any news about magnesium alloy in engineering magazine or somewhere? Yeah, they are trying to replace aluminium with magnesium because lighter weight, wherever possible, not all, okay? Because it's a lightweight, fuel efficiency badega, right? But processing magnesium alloy is very difficult. It catch fire easily, not parts while processing, melt handling and all, right? So that will make it a limitation. Okay, now you felt density. You might have read, you might have got out marks in your, that what is the material science and engineering subject, huh? Right now, but you didn't remember, you didn't feel it. So now you felt it. With respect to different material, if you see, you will remember nicely. Arey bhai, ye lightweight hai, arey ye heavyweight hai. Why titanium is so popular? Titanium alloy. No, biocompatibility is, there are many materials which are biocompatible, okay? Huh? Strength, weight to strength ratio. See, you are saying that, you are not realizing it. So if you realize it, you would have told what is the titanium density. Right? Steel, see, why not steel? Strength तो है, लेकिन weight ज़्यादा है. Titanium weight कम है, strength almost similar to steel है. तो कौन सा choose करोगे? Obviously ये choose करेंगे. But cost expensive है. समझ में आया? So wherever you are okay with the cost, you use this. Wherever you are not okay with the cost, then come back to steel. Same वही चलता रहेगा. ठीक है? Understood? So when you say weight to strength, this is the correct answer. You will get out of out. But when it comes to application, you have to use that. What is weight to strength? Okay, weight, strength. Okay, why weight is just density. So why it is density? Because steel से आधा है. So all those things should come, right? So that's what, from where we went somewhere. So percentage density. So percentage density is a density, actual theoretical density, what you searched in your Google. The वो denominator में रखो, whatever you measured density, वो numerator में रखो. That percentage is what we are showing there. It's called relative density. Percentage density, relative density. 100 minus that is a percentage porosity. Right? Okay. Now you will ask, where is that numerator density came? This came from literature. That वो कहाँ से आया ऊपर वाला? That no, this is okay. I'm talking something which is not there.
The point is, at 0% overlap, the percentage density, relative density is very low.
Yes, 97. That's what this is a porous. So you can see this micro. There are porosity here. There must be overlap. That's what you have to optimize that. I told you if it is aluminium, melt pool width will be very big. Steel melt pool width will be less. You can't put same overlap everywhere. So you have to know your single track width. Then you have to try some percentage in that range. Then you have to set, okay, this is my what I want. Right? And you can't end up with one parameter. You should have window of parameter. Because somewhere you need something, somewhere you need something. Because I told, क्या बोलते मग्गू डालते वक्त, so border parameter अलग रहता है. Border you will make by some, then filling अलग रहता है. So those things again parameter will change here. Within a layer, border, support structure, infill, and hatch. There are different sectors which will need a different combination of parameters. That to optimize one for that. Right? Okay. So that's how you have to choose proper hatch distance. What I am talking here. Once hatch distance is fixed, then same thing will apply on layer upon layer. Then your part is ready. Right? Now we are getting into microstructure and post heat treatment. Now part is ready. Now whatever best you can do in the machine you did. But now when you take out the part, when you cross section, you see, if you see up to distal, you will see like this. This is S13 tool still, okay? You will see like this. And this microstructure, if you zoom in with the SEM scanning electron microscopy and all, you will see these features. This is one zone, this is one zone. Means within one melt pool, wherever dark is there, you will see this. Wherever light is there, you will see this. Here, can you see dark light, dark light? So now what is it? These are all different zones within around the melt pool, exposed to different level of temperatures. Within 200 micron, 300 micron range, you will get patch. Is it okay for the application? No. Why this happened? Because of rapid solidification happening in your process. Laser when melts, entire heat will be taken away very fast. Do you know cooling rates? Do you know quenching? You might have heard quenching. You know tempering? What is it? Very well. Yes, we know. Fine. What is tempering? What is quenching? Yeah. So that is a process. Dipping the liquid, oil, air quenching, furnace cooling. They are different. What is the maximum fastest heat removal in this? Depends upon the thermal capacity of the liquid you are using. That's why there is a water, oil, different types of oils. So what is the maximum possible? 300 degrees per minute. The maximum possible. That is a conventional limitation. Even though I know if I increase this, I will get best microstructure, but I don't have anything to increase it. Understood? So that is possible by this process. There we are talking maybe 1000 degree per minute, let us take. Here we are talking orders of that. 10 to the power of 4, 10 to the power of 5 Kelvin per second. उस तरह का cooling rates will end up with these kinds of microstructure. These are called dendrites. Equiax, columnar dendrites. Heard dendrites? Yeah. Okay. So this is equiax dendrite, it's a columnar dendrite. But this is not okay for my application because this is a segregation of phases, these are all. So that is not good for the application where, for what I am doing this. This is a S13 tool steel pressure die casting die. It's a thermomechanical fatigue. The material, the die will go to 200 degree to 750, then 200, then 750, 200 in 30 seconds. And with a load of aluminum melt pushing inside with the 200 and 250 MPa. So that is thermal and mechanical cycle fatigue. So these kinds of segregations microstructures will not do, it will crack and it will break catastrophically. So we have to diffuse these. How we'll do? We'll do heat treatment. This is the microstructure similar. If I do different temperatures for a given time, I study all these things. We study all these things in our as a part of R&D. We subject, take it. एक दिन ये टेम्परेचर एक घंटा, एक दिन ये टेम्परेचर एक घंटा. Every day 1 different temperature. We will generate entire graph, different time, different temperatures, everything. Then we cut them. We see the microstructure change. This is the microstructure we achieved after heat treatment up to 650. From this to this, diffused, all gone, and their bright spots are carbide precipitates. That's what we need. Now will it end here? No. After that we will check it, what has happened. So this is the hardness we measure here, each microstructure after the exposing temperature. You can see there is a temperature, there is a hardness and then temperature. We plot that, it's called tempering curve. Any material you buy from the market, they have to give this tempering curve data sheet. Material come with data sheet, they will have tempering curve. So we generated tempering curve for our AM sample because our microstructure is different. So we generated that. Can you see the shift? This is the advantage we got from rapid solidification. Yes, rapid solidification led to the segregation, dendrites aaya, problem hai, but the microstructure is very refined and very super saturated. That is called quenching. Quenching के बाद tempering. तो tempering क्यों करते हैं? Quench से ये आता है microstructure. Then you temper, then it will diffuse. Then you will get secondary carbides. But our quencher microstructure is as-built microstructure because our rapid solidification is inbuilt, part of the machine. I don't have to do austenizing and quenching. I will go directly tempering, which they do second part. So when I do tempering, I will get very fine, carbide and martensite, which has shown this shift. This is a resistance of a microstructure to soften. So this shift has increased the service life of the material. Now, additive manufacturing, two advantage in this material. Microstructure improvement. Second is geometry, complexity, conformal cooling channel. All those come from the manufacturing point of view. The solidification helps in microstructure, which will increase in service life of the die because of this shift. Because microstructure is not giving away. Can you see this shift? So it will take more and more load, more and more. I can survive more, like that. So the microstructure getting tempered is the reason for die failure. So do XRD, we do residual stress. Can you see the as-built has tensile residual stress? Do you know residual stress? Residual stress. You know tensile and compressive residual stress. You know pinning. Pinning. Short pinning. You know short pinning. What is that?
Bombarding with the ball.
No. Why is that? Why you do that?
To improve the property.
What property?
Surface property.
What surface property?
Just like a hardness.
No hardness. Tell something else. No, hardness maybe, but depend upon the material, but the purpose is different.
Hardening the structure.
No. Yes, but it will affect what ultimately? It will not alter the structure, but to some extent, yes, I can't deny that. But to relieve the internal stresses or to induce the stresses. That's what I told, two types of stress: tensile stress, compressive stress. So tensile means you are already going towards failure. Compressive means you are going away from the failure. So compressive stresses are required. So your short pinning will induce compressive stresses on the surface. Means you are going away from the yield point. Means you can take more and more stress. Zero से उधर जाना easy है या minus से इधर आके इधर जाना है. So that's what it is. Right? So you need compressive residual stress. And if you have tensile means you are already zero से ऊपर है और easily चला जाएगा. So that's what it is. So these kinds of microstructure.
That means compressive residual is big part. Its tensile property will improve.
Yes, supposed to be. But you are doing a short pinning on surface. I am talking bulk. And tensile property, what you are saying is a bulk property, not surface property. Be clear with that. You don't expect that you do short pinning and you do tensile and it will be, there will be much difference. There will be little difference. You have to identify that. Or you have to do indentation, nano indentation, and do that and see whether it is really helped or not. But bulk wise, I am talking now. So this is a bulk microstructure, compressive residual stress. See, this is a tensile. See, 0 se above hai. I am near to yield strength. This is not okay at all in any case. So when I do heat treatment, see 600 and 650, it has induced compressive. Why? मैं तो short pinning नहीं किया, खाली heat treatment किया. कहाँ से आया compressive residual stress? Tensile कहाँ से आया first of all? Because my rapid solidification has strained it. तो टेंसाइल है अभी. मैं हीट ट्रीटमेंट करूंगा तो ऐसा हो जाऊंगा. तो माइक्रोस्ट्रक्चर बीसीटी से थोड़ा सा रिलीव्ड हो गया. और आई हैव सो मच सॉलिड सॉल्यूशंस व्हिच आई एम रिलीविंग एंड ड्यूरिंग हीट ट्रीटमेंट एंड आई एम गेटिंग रिलैक्स्ड. एंड ड्यूरिंग दिस प्रोसेस आई एम श्रिंकिंग because something sitting here has gone, so I am shrinked. So that will add to compressive. When something expands, see when there is a bend, आपका strength of material में होगा ना, तो ऐसा जब bend होगा, इधर compressive आएगा, इधर tensile आएगा, कुछ है ना, वही formula. तो जब वो A हो जाएगा तो compressive. So that's why the heat treatment has induced compressive resistance. There's no pinning here, no short pinning or anything. So that's what we observed. How this has reflected, you can see here. This is conventional S13, no additive manufacturing. Conventional. This is additive manufactured without heat treatment. This is heat treated. Means we got this, then we got this after heat treatment. That is this microstructure. Means this is this, this is this, this is this. You can see the highest yield point, but you lost the elongation. Right? It go and break ho gaya. But here it go like this, little less yield, but it will go longer. So you can see this is matched, this is almost increased. I am comparing with conventional to 650. This is no way okay. This is not okay with respect to very high strength, but elongation has gone because I need toughness in this application. And this microstructure is not at all okay, so I am denying this. But this to this, yes. If you compare these two, but strength is same, everything is same. Why additive manufacturing? But we have design freedom, design advantage, plus microstructural advantage, which will retain the microstructure for longer time and increase the service life. So this is what I proved in this, and this is a PhD work. What I said, sir, IIT Chennai. That guy did PhD work. We have 4 papers on this work. Right? So we took this to next level, industry. So we went to industry, we asked them, please give us one component which really, where it matters a lot. So they gave us a pin like this, 210 mm. These channels were not there. Cooling channels were not there. It was literally, sent to die. It will expose everything and it will do maximum and it will die. It is dying, means they are changing this pin every 2000 shots, pressure die casting pressure. Every 2000 shots, they have to shut down, they have to remove everything, change the pin, place the new pin, and then start. Almost one shift time, they will lose it between this. Right? So what they told is, can you do this? So they gave us, this is about 22 mm, this is about 8 mm, this is varying diameter here. So as it goes here, it's almost 13 mm or so. So 13 mm में हमको cooling channel बनाना है. तो हमने 2.5 mm diameter का cooling channel. That's why one is straight, one is spiral. I don't have much space. That's why I can make only one spiral. So we made one spiral. There is a thumb rule also. So you can't just go too close to the surface so that it will puncture in the process. That is also not allowed. So we took their suggestion because they are regular die designers, and they gave us some thumb rule. Within that, we just deviated little bit here and there, and somehow managed to make 2.5 spiral up, then collect here and then come back straight. We added this feature in design. Then we built that thing. Before building, we tried how it will be inside and all. Can you see here spiral? It's like, from here it is going here, from here it is going here. This is upper portion, cut portion, it is coming like this. And we saw what is exactly here because it's complete overhang. I can't use support structure there. It's just built like that. We just, okay, that is okay for them. It's not a problem. So we went with this. Then we built. This is the X-ray of this pin. Can you see a spiral going and then straight coming back? But here it is a thicker diameter. I can't penetrate X-ray here. If I penetrate here, this is going. If I penetrate here, this is going. I have to choose either one of them. So I thought I will choose a spiral one because here it's almost straight line. So no fun in that. So we choose this and we made 4. I told you we give some allowance. We gave allowance. Then we machined it. This is the final pin ready. This is the cast part what we cast. Right? So this is what you are seeing. This is the aluminum part which is made from this pin. This portion is made from this portion. Actually cut section of the part. The part, there is a hole. Can you see? There is a thread, there is a hole, there is a something. So this pin will come and then cast part will fall down. Then pin goes, then aluminum comes, solidify, then cast part. So that's how it is. Now next slide you will see the results, how it performed. We took it to the industry, we placed it, and then there are 2 special lines were given. You can see the temperature drop between the shots almost by 10-20%. Then you can see the rejection becomes 0. You can see even after 6,000 shots, this is their pins, this is our pin, no defects. And they gave us a certificate saying that this technology really works. And we saved one more thing, because of this temperature, they saved 4 seconds per shots. It's written somewhere? No. It's published in this journal. They saved 4 seconds per shots. So 4 seconds per shot means each shot is 30 seconds. So every 10 shots, they are making 1 more shot extra. So that kind of, and it is surviving 6,000 shots, before was surviving 2,000 shots. So 3 times production plus that second time saving. So this is a certificate, this is a Castal industry which we worked in Hyderabad. And they gave a acceptance that, okay, this technology works and this helped, this saved our production time and all. Right? But the cost, if you compare, what is that conventional pin cost, what is your pin cost? I will not tell my pin cost, but I will tell you conventional pin cost. That is 2,500 rupees per pin for them. But if they try to achieve conformal cooling channel, I don't know whether they will be able to do that in that pin. But we did that. Ours is little expensive, but if you go for production, I showed you 4 in one go. If I put 10, I hardly increase by 2%, maybe 10% of the build time. But it will be expensive, yes. But we demonstrated this, but it matters a lot in terms of long run. This is another thing. So I told you 210 mm. So there is some straight line portion. Why I will do additive manufacturing of that? Now I am coming to cost saving. So let's see where I can save. So usually if you see pressure die casting, I don't know whether you have got a chance to visit any pressure die casting industry. With big bed, almost half meter by half meter, this much thick. And it will have a lot of straight cooling channels. It goes 90 degree, comes back. So this much thick, and then on that only thin, hardly 10 or 20 mm height features which will give the shape to the cast part. So then I told, okay, I don't have to build the entire thing. You bring me this solid block, and that I will build only 10 mm, 20 mm. because that's where additive manufacturing is required. Otherwise, why you need additive manufacturing to build a solid? So to prove that concept, how the interface works, this is AM part, this is conventional part, then do heat treatment. There's a lot of study. This is published in this journal, and you can see people who are interested in PhD and all. This is a conventional microstructure. This is EBSD graph. Okay, conventional microstructure. Can you see big grains? This is soft anneal. This is additive manufacturing. Can you see fine grains? When I do heat treatment, this become coarsen, this become finer. Right? This is a conventional microstructure. This is a AM microstructure has become like this. Now, can you see difference between them? Not much. So that's what you will see here. This is a phase diagram. This is a color orientation diagram. So here blue things are retained austenite. Have you heard austenite? Ferrite, martensite, austenite. Yeah. So this is a retained austenite. This is a conventional soft anneal. There is no only ferrite. When you do heat treatment, all these things have gone. That is another advantage of heat treatment. These are all dots are carbides. Okay. And again here no carbides. Here there are big carbides, few, but here you will get fine many. So this microstructure, if I subject to hardness, you can see this is conventional, then hybrid, this part and this part. After heat treatment, this shifted here. Right? Then when you do a tensile test, you see this one, AMQT, additive manufacturing quenched and tempered, 9.6, this is 20, this is 9.6. So we are near, but previous slide I showed you 14, now I am telling 9.6. Yes, there is a problem, but where is the problem? Problem is away from the solidification, aluminum melt solidification. I told I have solid bed and I have only 10 to 20 mm which is exposed to the aluminum melt. I am away 20 mm from that exposure. So these kinds of property could be okay for there, but not on the surface, but far away from the aluminum solidification should be okay. But this has to be proven. So to demonstrate that, we took one conformal channel, we took a straight line, then the challenge here is you have to match them in additive manufacturing. It's not CNC or robo or something where you have 0, 0, okay, from here I will go and I will exactly do that. It's not happening in powder bed additive manufacturing. You have to have 0 clamp, you have to position it. It's very challenging to exactly match that center and print on that. We tried our best with a 0 clamp. If I go to OEM, they will charge you too much for this. So I made my own. We are in 100 micron range. That will be covered in allowance. Right? So I'll go fast little. So now onwards, it's just application. I'm not going in detail. So this is a missile. Can you see here? 4 boosters which will position the XY. This is moving direction. This is XY direction, right? Something like this. If I disassemble this, you will see this part. Hope I have that video here. Yeah. This part will come out. Yeah, this part is this part. I am making that, not entire missile, okay? Only that part. They gave us this part. Please do this. We told this. You can see here 50% weight reduction. So in a missile, if you reduce even 10 gram also, it matters a lot because you can add so much fuel and it will fly so much time. So 50% weight reduction we proposed and they accepted it. In 2 materials we are supposed to do. These are all test coupons we made and established the properties. Right? While building that part, we face so many problems. See, cracks here, so many cracks here at different heights. If you map those cracks, this is what is the real R&D and expertise what you call. So fail हो रहा है छोड़ दो नहीं होता वो एक है fail हो रहा है क्यों हो रहा है हम क्यों नहीं कर सकते. So what measures can be taken? So for that you have to understand the numbers, where exactly, how exactly. So there is a pattern here. Wherever sudden change in the area, there we are getting a crack because of a variation residual stress and heat added to the next layers. So that we managed I think this video is okay. It's coming, no coming? Huh? This is the part. This is a simulation what we did. These are support structures we have to give. Red color are support structures. So this we virtually see before printing. Is there any problem and all? Then actual printing now. So layer by layer it is getting printed. It's quite fast, but it's not that fast in actual. You can see support structure getting printed there. It's fine things. So this is a withdrawal of the part. There's a loose powder here. We collect back. This is the component. So support structure we are removing here. Can you see a support structure being removed? It's almost 70 mm inside. This part is 120 mm by 120 mm by 120 mm. So we delivered 8 of them. Each was taking 27 hours. One part 27 hours. If I build together, it may go up to maybe 35 or so. Two parts I can build in my machine at once. So these are the 8 parts. This is how it is. Along with each part, we have to build the test coupons. Can you see support structures here? So these test coupons will go with this until end. Okay, they will test these things and they will accept. Then they will accept the part. Then they will see the part dimensions and all. Right? So these are all CT scans. If you are interested, I will just play. It's playing. Yeah. So it's CT scan in this direction, CT scan in this direction. Right? So this is another material, BJD12Y Russian alloy. We got the ingot and we made the powder and we showed how it behaves and all. This is again IN78. We took a Midhani. Do you know Midhani? Midhani is a Indian alloy making industry for defense, and now it is open market. So they will give for private also. So they make alloy. They have their own IN718. So we took that ingot and made powder and demonstrated that it works. This is all post heat treatment of IN718 manufacturing. So we study. This is published in this very prestigious journal. So heat treatment will give these kinds of microstructure from this microstructure. Just little change in temperature will matters a lot, right? And application also needs some particular phase to be there to achieve what they want. And this is another titanium alloy, another PhD in NIT Warangal, Narsaya sir is now doing. We have a book chapter on this, and one more paper is getting ready. This is interesting. This is a biodegradable implant. You haven't heard titanium? That is the only material. Do you have heard any bio implant material? Steel, stainless steel, cobalt chrome from dental application. 3, pneumonic also, yes, maybe stent and all. 4, any other material? This is another material, iron manganese alloy. There is one more material, next slide, magnesium alloy. Okay. What are the common thing in these alloys? They are all non-magnetic. They have to be non-magnetic because you will do, right? Sir understood. Right? That is the basic property. Anybody asks bio implant ke liye material how you will select, first point you should say it should be non-magnetic. Should not be, because you are subjecting a body into CT scan, X-ray, wherever you go, airport and all, right? So magnetic nahi rahna, nahi to chipak jaoge kahin.
Only reason should non-magnetic.
Yes, because it will interact. If you are in air, you will get stick. Not like that, but yeah, it will affect. So it has to be austenitic, not ferritic and martensitic. So you have to choose the alloy element so that you will not end up with a magnetic phase. So it should be non-magnetic. So that's how it is designed. This alloy we have patent, right? We made this alloy and we powder made microstructure. We are getting cracks. We found a parameter without cracks. Then we made so many components for different biodegradable study. Even we are going to put it in a rat and all. Right? These are the final material, final components the doctor wants. Screws, elbows, bones breaking, and they put a screw and they will fix it. Biodegradable means it will disintegrate there itself. You don't have to operate again and remove it like titanium and steel. It will get into your body, no need to operate again within 8 or 12 months or so. Biodegradable, that's why it's called biodegradable. Whatever you say, titanium, cobalt, they are not biodegradable. This is biodegradable.
Magnesium.
Next is magnesium. Yeah. Sorry. This is magnesium alloy. Magnesium, yttria, zinc. There are 2-3 magnesium alloys. This is one very rarely studied. We made ingot, we made powder, then we studied what are the parameters, best parameters, then we made so many things. This design is different than previous one because this will be used in different parts of the body for different purpose. That screw will be used for different part of the body, different purpose. Right? This is the intensive parameter optimization.
When they are designing the body, that affects the how are they expelled from the body?
Some alloys, magnesium, see, zinc, magnesium, these are all part of your any supplement, right? So those are chosen like that. And if anything which is not accepting body, it will go out without affecting your body, right? So we established the mechanical property required for this application. Don't think that it's less and more, but application ko kya chahiye wo to hai. This is one more work. I will not touch this. I will skip this. This is a dissimilar material. So this is a iron 78 and stainless steel. How that is working and all we studied and we published this nicely in a good journal. It's not written. It's written there at the end. And this is another work, copper to steel, very difficult to weld. We did additive manufacturing nicely. You can see it broke here in the copper side and the interface is still intact. This is accepted by very prestigious journal. It's very difficult to publish in that. And it took almost 14 months and 5 iterations of review. Very difficult. But somehow we managed. This is another hybrid. So this part is almost 60-70 mm height, but features are only 5 mm on the top. So what we did is, we took the rod and that we made this 5 mm. Then we held this, you can see the check mark here. We held the AM part and we machined the remaining. And we added these threads and all. Then this has gone into the shaping this aluminum foil bundle. So if I make additive manufacturing as it is whatever they gave, it will take 6 hours. I made 2 hours, even less than that a part, but post machining of maybe 600 rupees, 2 hours, 3 hours, you will machine it and you will thread it in one lathe setting. Right? So like that also we can save the cost, still taking advantage of additive manufacturing. This is another complicated one. So I will just show you the X-ray here. This X-ray has, this is 2.1 mm thick plate. These channels are in 3 layers and placed between 100 micron each. Micron. There is a slit here. Can you see here? Thin slit here. That is 300 micron slit in 2.1 mm thick plate. It's used in hydrogen oxygen fuel cell bipolar plate. This is another application used in some defense application, very critical. And these are all other parts. This is a micro heat exchanger. This is a NGV. You saw this aerofoil in your lab, right? So this is a NGV. This is something which we made overnight. BDL Vizag got some machine and this parts imported machine. These 2 parts were broken. So they were installing and foreign nationals were there to install and they wanted it to be Friday problem hua, Monday wapas chahiye. So we took a broken part, we reverse engineered, We got the drawing, we made some modification, we printed them on Saturday. Sunday उनका आदमी आके हैदराबाद आके लेके गया. So Monday it was working. So these kinds of things also you can do. It's in aluminum alloy, not much expensive, but the part criticality and the time and the foreign nationals sitting in India and they are just waiting for these two simple parts. This is used in a reduced pilot scale nuclear reactor, BARC. Entire project was holding up because of that. This is stainless steel part, very critical. Conventionally they were struggling. We just made in 3 hours, 3 of them, and we sent them without any. They were surprised and they were saying, what? They were very happy. So those things we did. Yeah. So I told we have worked with many powders. So whenever we change powder to powder, we have to disassemble entire machine, clean them, ensure that no residue of powder is there, and then place new powder, assemble back and place new powder. So it's almost 1.5 day process whenever we change one powder to another powder. It's not easy, so we schedule it and we take one by one. This is our team. Thank you. This is one more application here. It's cracking like this. We solved it. It's a M2 tool still. The patent is in process. So only 2 or 3 people working in the world. So we have cracked it. I mean, we made it success. We're working on that.